Let us start this lecture with a thought process from the Donald Hane, and who says that any theory claiming to describe how organisms originate and continue to exist by natural causes must be compatible with the first and second laws of thermodynamics. So, if you look at it, it really has given a very great dimension of the first and second law of thermodynamics, and which we are discussing particularly for control mass system. In the last lecture, we have taken isobaric process, that is the constant volume process, and isobaric process, that is constant pressure process, and seen that how you can apply the first law of thermodynamics for both reversible and irreversible processes. And in last lecture also we defined two terms, which is basically the specific heat at constant volume and specific heat at constant pressure, and those are basically properties of the substance. And one can also look at, although historically people have defined the specific volume at constant specific heat at constant volume as the change in internal energy, right, per unit change in temperature, and of course per unit mass of substance. And similarly they have defined for the specific heat at constant pressure as the change in enthalpy per unit change in temperature per unit mass of substance. But if you look at it, is basically instead of specific heat, people could have term it as a specific energy. And in the last lecture also we learned how to evaluate the Cp and Cv values, and we learnt also for ideal gas it is only the function of temperature, and of course for real gases we didn't look at, but it can be also function of pressure. So, it is quite complex to evaluate, and we will see also that one can take average values and then try to calculate, particularly whenever you are doing the hand hand calculations. But today we will also little bit dwell upon how we can use accurate values of the CPs and also compute and do the accurate calculations. So, if you look at, there are three ways of calculating the change in internal energy and enthalpy. One is you can use a table or tabular data, right, the data given in table like your steam table or the refrigeration table, like you can find out U and H directly and then use it, right, which will be give you the more accurate values, right. So, if you look at, one can find out, like particularly let us say internal energy, I can find out internal energy from the table, steam table, or internal energy from the again steam table at a particular temperature or a pressure kind of thing. Of course, keep in mind that in some book this internal energy for the steam and the refrigeration given, but in our book what we are following, it is not given, it is the enthalpy what is given. So, for that one has to find out enthalpy, like and then from use enthalpy data, of course one can find out internal energy, that one can do. There is another way of doing, like Cv and Cp, either Cv or Cp can be related to a temperature, right, and then you can have a polynomials, as I told, a third order polynomials. For example, if I say Cp, I can write down A plus B T plus C T square plus D T Q, right. So, if you look at, if I get this coefficient, and this can be like coefficients A, B, C and D. So, these are coefficients or the constants, right. And if I know these things, I can evaluate, integrate the equation very easily, right. And keep in mind, this I have written I, this I can be for like any other spaces like O2, it can be S2, it can be S2O. See, for different species or different substance or gases, it will be different. This A, B, C and D will be different. Okay. So, I can have a table, or I can feed this data and then integrate it and get a very accurate, and particularly when you are using computer to compute your values, right, then one can manage, but hand calculation, it is quite difficult, it will be time consuming. And there is another way which we will be doing, right, that is that you take some average values and keep in mind that the change is not much, the temperature is variation is not much, and then you take average values and calculate, right. And what we will be doing, we will be most of the time will be using this, that is you use a steam table or a refrigeration table or any other kind of things data value. And we will be using also what you call average values kind of things. These average values we will be taking and using that. We will be using this and this most of the times. Of course, this average values you will have to sacrifice the accuracy, but it will be good enough when you are doing some engineering calculation. You need not to worry too much about the accuracy hand calculation you are roughly doing. And sometimes we may learn how to handle this using a polynomials fit kind of things. People are having some experimental data people have generated, and then they have used a polynomial fit, or from the statistical like thermodynamics one can find one can find out the properties. So, as I told, this is the how we will be handling the gases, right, which are properties for these gases. But let us look at now the internal energy and enthalpy and specific heat of solid and liquids, because if you look at these, solids and liquids are incompressible in nature, and therefore specific volume will be remaining constant in this case, right. There will not be any change as such of the density kind of things. As compared to the gas, the change is very negligibly small. We can assume it to be to constant. So, as a result, the processes what you call the specific volume will be remaining constant kind of things, and therefore we can take the Cp and Cv as the same. There is no difference between Cv value and Cp values, because there is no change in the specific volume, and which is equal to the specific heat. And let us say for iron, you can say that is 0.45 kilojoule per kg degree Celsius. If you look at I have asked this question, when you increase this temperature of 1 kg of iron from 25 degrees Celsius to 35 degrees Celsius, what will be the amount of heat you will have to give is basically 4.5 kilojoule, right, isn't it? This is because the mCp dt, like if you look at the amount of heat will be mc delta T, because this iron. So, this is 1 into 0.0 4.5 into the change in temperature is, it is going from to 35 degrees Celsius, right. So, it is 10 degrees Celsius. So, it is 4.5 kilojoule. But if I do this water, 1 kg of water, and I am changing the temperature water 1 kg of water from 25 to 35 degrees Celsius, it will be around something 4.41.8 kilojoule kind of thing, isn't it, because your Cp value is 4.18, right. So, it will be 41, it is something 9 times that of the iron. That means the heat capacity of the water is higher, right, than the iron. So, now let us look at another process is isothermal process, where the temperature will be remaining constant. So, what we will do, I mean like we will take again piston and cylinder arrangement containing gas, we will have a constant heat what you call bath, and you keep in that this is having temperature here, and then there will be some heat transfer will be taking place, right. This is the heat, and what will happen if the temperature, and we want to keep it temperature of this gas, that is the system, this is my system, right, constant. So, what I will do, that means the piston will be moving and such that it will be remaining constant the temperature, and we can assume this process to be isothermal, provided the temperature gradient between the what you call constant bath and the gas is small, and so also the change in pressure, this thing will be very very small. I mean it is tending to a 0. It is like you can think of putting a sand grain and then removing one grain and keep the temperature constant of the system, like you can assume that way, and then the process can be considered as a reversible process, because you can reverse the system after the change to the original one, and you can describe the process from 1 to 2. And this process, if you look at, it is basically what happened, it has been expanded, right. So, this is the work being done, and applying the first law of thermodynamics, we can say that d U is equal to dq minus dw, and this w is the PdV, that is a change in the volume. So, therefore, that is having, and in this case temperature is remaining constant. Therefore, what will happen to internal energy? Internal energy will be what? Will be 0, right, yes or no? Because the change in we have seen that. Keep in mind that if you want to estimate this W what it will be and the Q kind of things, then we need to know the properties, and we can assume as the ideal gas. We can also use then we will find out work done, basically PdV, which is nothing but RT by V d into dV, and when we integrate this between state 1 to 2, I will get RT ln V2 by V1, and we are assuming the process to be what you call isothermal. So, therefore, I can do it very easily. And as I told that du is 0 because isothermal process, therefore, dq is equal to dw, and when we integrate this will be work done between state 1 to 2 will be RT ln V2 by V1. And for an ideal gas, dq is exactly equal to the work done for an isothermal process. And I mean like this is about the isothermal process when we considering the reversible, right, and we will consider the adiabatic process where the heat interaction will be 0, like we can take the same our what we call paddle wheel example, which is being rotated in the this kind of a rigid vessel, and then there will be, because of this work done, and then there will be change in the temperature, and then kind of the gas, if I consider as a gas, and but this process will be not reversible. I have told earlier, right? It will be an irreversible process. Let us consider the, I mean, like electrical resistors, and this is work, what you call some work is done by the system and surrounding whenever we put the switch on, and it is insulated. So, no heat is going out, and this process is basically taking place adiabatically, and it is an irreversible adiabatic process, of course, during which electrical work is being done. So, we can apply the first law of thermodynamics, that is du dq minus dw, and this dq is basically the 0, because the adiabatic process. Therefore, the work done is equal to change in internal energy. In this case, the internal energy will be increasing of the system. So, let us consider the another case, that is rigid and adiabatic wall. Two chambers are there. One is the gas chamber at a pressure P and temperature T, and there is another chamber which is at vacuum. Now, this is the partition, and if this partition can be removed, then what will happen? This gas will be expanded, right, and this is a insulated one, that means no heat is going out, right, that is 0, and it is rigid one. And what will happen to the work done in this case? What will happen to work done? Work done also will be 0, because there is no PDV work, and right. And however, the pressure will be reduced, right, and we can apply the first law of thermodynamics. In this case, what you call the work done is 0, and the heat, because adiabatic process, that is also 0. So, therefore, there will not be any change in internal energy. Internal energy will be remaining constant, right. Let us consider another case where the gas is at pressure P A and temperature T A, and in another chamber, like other chamber, gas B is at pressure P B and T B, and keep in mind that let us assume that like P A is greater than P B, okay, or it can be other way around, P B is greater than P A, but let us say that pressure P A is greater than P B, and it is separated by a partition. I can remove this partition, right. If I remove this partition, what will happen? That gas will be expanded from high pressure. This is, let us say, high pressure, right, high pressure, right, and this is low pressure P B. Then what will happen? Some work is being done, right, because all the time this is giving a resistance, so that work is being done. And in this case, as I mentioned already, the adiabatic wall, that means the heat transfer across the system boundary is 0. So, therefore, if we apply the first law of thermodynamics, this case the change in internal energy will be there, which is nothing but the work done kind of things, because get the gas. So, this is also an irreversible, both this example what we have considered is basically irreversible process, right, and you can apply the first law of thermodynamics and then can do that. So, let us look at not only the adiabatic process, but also the reversible process, what we call it as a isentropic. And there will not be any heat transfer across the system boundary, and it is reversible. We will consider again our what we call piston cylinder assembly, and then which containing gas, aspirator pressure P and T, and it is insulated. So, therefore, no heat being transferred, and this what you call, if you the atmospheric pressure or the pressure which is acting on the piston is reduced little bit, I mean by the small amount, then the piston will move upward, and then there is no heat transfer. So, it will be expanded, the gas is expanded because the pressure here, the system is higher than the its surrounding. And if we will apply the first law of thermodynamics, that is dU is equal to minus dW, because if you look at dQ in this case is 0, right, and the work done is nothing but your PdV. So, therefore, dU is equal to minus PdV. And keep in mind that system does the work on its surrounding at the expense of its own internal energy, right. And equation 1, if I want to find out, I want to integrate, then I should know the relationship between P and V, right. But this is a generalized, it can be applied for anything, but if I consider the ideal gas, it will be very easy to relate this pressure and P and V by that P V is equal to R T, and we can integrate this equation 1. So, if I can do that, this work done also will be basically what we have seen, this work done is equal to change in internal energy, right, and that is CV T1 minus T2. We have already seen that in that. And if I take the ideal gas, where U is a function of, for ideal gas, U is a function of temperature only, right. Therefore, I have taken, and for an ideal gas we know that H is equal to U plus PV, and that is equal to U plus RT. And if I integrate this like from the definition of the Cp values, dou H by dou T by P, I can use this expression over here and then find out dou U by dou T at a constant volume plus equal to the RT. I can this thing, and this is basically nothing but your what you call Cv, right. So, I can write down Cp is equal to Cb plus R. This will be using very often. If I know the Cv value for an ideal gas, I can very easily calculate the Cp and vice versa. So, if you look at gamma, gamma is basically ratio of Cp by Cv, and we already know that Cp is equal to Cb plus R, then I can find out basically is equal to 1 plus R by Cv, and then that is nothing but Cb is equal to R by gamma minus 1, and once we know that from this definition, I can find out Cp is equal to gamma R divided by gamma minus 1. So, if you look at, if I know this gamma, and generally for the gamma for air is 1.4, right, and of course, this gamma will be different for different kind of constituents depending upon whether it is a monomolecular or a dimolecular or polyatomic diatomic or monoatomic or polyatomic substance, right. So, then what we will do, we can integrate this, we can evaluate this work done between station 1 to 2, state 1 to 2 is as PdV, and we can put this is which is equal to the CV T1 minus T2. Okay. So, if you look at this work done, we can in place of the CV I can take that R by gamma minus 1, and if I look at this R T1 is nothing but your P1 V1 from the ideal gas law, and R T2 is nothing but P2 V2, and therefore, the work done will be is for an isentropic process will be equal to P1 V1 minus P2 V2 divided by gamma minus 1. And let us find out relationship for an isentropic process, that is CV dt is equal to minus P dV is equal to from the ideal gas law you can find substitute this P with the RT by V into dV, and so if you look at, I can write down express this expression as dT by T. I can take this T here, or I can divide by this temperature here, and also CV here, and this side CV and T. So, this will cancel it out, and then you will get RCV and then dV by d2. If you can integrate between state 1 to 2, and you will get that very easily, and these are you can take it out, it is not changing with respect to volume. So, therefore, we know that CV is equal to R divided by gamma minus 1. So, R by CV is nothing but gamma minus 1, and we can do that, and we can what you call integrate this expression as 1 to 2. So, then we will get ln T2 by T1 is nothing but equal to minus gamma minus 1 ln V2 by V1, and from that we can get this expression, which is very commonly used. T2 by T1 is equal to V1 by V2 gamma minus 1. Keep in mind that this negative sign is being taken in, so that it became V1 by V2 in place of V2 by V1 here. So, now what we will do, we have got a relationship for the isentropic relationship between the what you call temperature and specific volume. Now, we will be finding out relationship between the pressure and specific volume. For that, we will consider the ideal gas law again. PV is equal to RT, and that is equal to T2 by T1 is equal to P2 V2 divided by P1 V1. We can write down from that. And if you substitute these values here, like from this we know, and then values between what you call P2 by this one, and then because we have already derived that relationship, right, and we will say P2 by P1 in terms of that, and you will get V1 by V2 gamma minus 1. And because if you look at, I can find out this thing in terms of T2 by T1, I can put in terms of V2 by V1 power to this gamma minus 1. So, then we can evaluate is very easily that P2 by P1 is equal to V1 by V2 power to the gamma minus 1 into V1 by V2, and then that is nothing but your V1 divided by V2 power to the gamma, and that is equal to the PV2 gamma is equal to P1 V1 power to the gamma is equal to PV power to the gamma constant. So, this if you look at, this is the relationship what we keep in mind. So, that is easy, and you can also find out other relationships between that. So, let us look at the polytropic processes, right, and where it will be basically the various processes what we have seen, like your isobaric process, isochoric process, isothermal process, and what you call like adiabatic or isentropic process. It can be together, one can think of visualizing, and this polytropic process which you will learn later on is basically very important because you do not know really in actual system what will be happening. If you could know that, then one can use it. So, in practice there are several reversible processes in which heat is transferred across the boundary, right, and such process can be described by relation d ln p plus n d ln v kind of things. And if we integrate this above equation, we will get a relationship like basically p v n is equal to constant. We can get that, which is you can say that p 1 v 1 is power to the n is equal to p 2 v 2 power to the n, and n is the your coefficient, like your specific ratio. This is the polytropic coefficient kind of thing, n. That indicates this n is basically the index of process, like whether it is n can be various values, and like that we will see, like if it is n is equal to 0. So, what will happen in this process? If n is equal to 0, this will be which process? You can see if it is 0, v power to the 0, what will happen? This one, anything power to the 0, what? This is basically isobaric process, right. So, the specific work done for such reversible process can be given as in the similar way, like what we have derived for what you call isentropic process. Work done 1 2 is equal to p 1 v 1 minus p 2 v 2 divided by n minus 1. In case of what you call the isentropic process, like in place of n, gamma is being used, that is all, right. So, by applying the first law of thermodynamics to this process, we can have basically u 2 minus u 1 is nothing but q 1 2 minus p 1 v 1 minus p 2 v 2 divided by n minus 1. So, if you look at, you can apply this process and then get this change in internal energy and the heat interaction and the work done. And so, if n is equal to 0, as I told, that is basically the isobaric process, and if n is equal to 1, right, that is the isothermal process, right, and n is gamma is nothing but your isentropic process. Keep in mind that in this process, right, and in n is equal to infinity, this is basically isochoric process, right, isochoric process. And this portion, if you look at, it is basically expansion processes, because the change in the volume is increasing. Suppose you are at here and then you are moving toward that, then this will be what you call expansion process, and when you are in this quadrant is basically the compression process, because the volume is basically what you call, you can go from like a higher volume to the lower volume. So, if the process is this way, therefore, that process is compression process. So, you can have a process for example like isothermal expansion, isentropic expansion kind of things, and similarly you can have the isothermal what you call compression and isentropic compression kind of processes. So, we have seen basically how you can apply the what you call control mass system, how you can apply the first law of thermodynamics to the control mass system, and we have taken the various processes like your constant pressure process, that is isobaric, and constant temperature process, isothermal process, isentropic process, isochoric process and other things, and we can apply. And you can I mean very easily, and what we will be doing in the next class, we will be now looking at how we can apply the first law of thermodynamics for control volume process, where the the what you call mass will be coming in and going out, and there will be this thing, and so we will look at in the next lecture. Thank you very much.